Hello! In this tutorial I will explain how to interface RGB LED matrix with your FPGA board. In this video I am using DE0-Nano-SoC board from Terasic and 32x16 LED matrix from Adafruit. First, let's take a look on how a regular LED matrix functions. The matrix interface consists of row and column selection. The row selection is straightforward, so let's focus on column part first. In this example we have 16 columns. Each column is controlled by its bit from 16-bit shift register. First, we shift data into 16-bit register on each rising edge of the clock signal. Note: since this is a shift register, it only holds the last 16 received bits. Once you shifted all 16 bits in it, you should disable the clock signal. Each bit in this register will later turn its column on or off, depending on its value. After data is successfully shifted, it's latched on the falling edge on latch enable line. Latching data allows you to fill the shift register with new values, while old data is displayed. Next, select the row and eventually enable output. As you can see, only the LEDs on the selected row are turned on, depending on the latched column data. While this row is turned on, we shift new column data. Then we turn the output off, latch data and switch to the next row. We repeat this process for each color channel until the whole matrix is updated. This way we only turn LEDs on or off. For brightness control we use PWM. That means each column is updated several times per frame. For example, if LED is turned on 10 of 10 frames, it corresponds to 100% duty cycle. On the other hand, if LED is turned on only in 5 of 10 frames, its duty cycle is 50% and brightness is lower. That means, if we want 8-bit color resolution, we must update each row 255 times per frame. That is why you must use FPGA to achieve good frame rates on big LED matrix. The matrix from Adafruit consists of two parts, 8 rows each. That is why I have to drive top and bottom half simultaneously. Okay, now you know the basics, let's start with the project. Start new project and select your device. First, import the pin assignments. By the way, all project files are available on my Github. Now let's add on chip memory, which will hold an image for the LED matrix. In my case, I will need dual port memory in order to drive two parts of the matrix at the same time. For convenience, I want to store RGB values for each pixel at one memory address. This makes 24-bit long data bits. But since only 16 and 32 data bits are available, I choose 32-bit long word size. Connect the clock and reset signals and export both memory ports. In this project we will just need a clock and a bunch of GPIOs. Next, let's add the memory component into our design. The component signals are pretty obvious. There are two simple memory ports. The first port will control the upper part of my matrix, the second port is for the lower part. Next, map the component. The byte enable signal select if you want to access only first, second, etc. bytes of your data. In our case, we just need the first 3 bytes. Okay, let's add additional signals for the memory and the matrix itself. Here you can see the already mentioned matrix signals, such as latch, output enable, 2 signals for each color, etc. Now let's take a look at the main process. First, I assign the matrix signals to the GPIOs on my DE0 board. Next, divide the main 50 MHz clock. The matrix controller is a simple state machine. In the first state, we shift data in the 32-bit shift register. To achieve 8-bit color depth, each row is updated 255 times. If the color value is greater than the update counter, LED is turned on, else it's off. For example, if the red value is 100, the duty cycle for particular LED is 39%. If the data shifting is complete, disable output, assign a row, and latch shift register. In case new row is assigned, we have to wait until the row selection transistor is stable, before we enable output. After this process is repeated 255 times, switch to the next row. Alright, let's add QSys file into this project and compile it. In case you want to preload on chip memory, you have to create initialization file first. Edit, save and go back to QSys. There you can select this file for initialization. By the way, if you like this video, give it a thumbs up and subscribe. Finally, let's program the FPGA.